Okay. Good afternoon, everyone. Welcome back to the class. So we will recap a little bit of what we did in the previous class rather, and we'll start with the introduction of what reinforcement learning is actually. Right? Earlier we stopped about what reinforcement learning was and how does it fit into the different fields of study, right? In terms of AI, where does it fit in terms of other fields of study like economics, mathematics, science, engineering, where does reinforcement learning fit? So just to take you a step back and come back to the point of what reinforcement learning is. So you will hear these terms repeatedly and many times during this class, okay? Agent, environment, reward, action, and observation or state. I'll be using the word observation or state interchangeably, okay? So what each component of this exactly mean? Let's start with the agent itself, the most important part of the reinforcement learning algorithm. Agent, in most cases, is, or rather in this case, because the course is focused on control, it most often is a robotic platform itself. Say, in case of a problem where you are working with UAVs, the UAV itself, the multi-rotor itself is the agent. You are working on autonomous driving, then the car itself is the agent. So you understand the concept, right? Now the robotic system itself is the agent. Anything outside the agent is the environment. The obstacles, the other drones or other cars that you find on the road, or whatever the other factors that might influence the agent is the environment. That forms the environment. And then you have the action. Action, by its name, like I said in the earlier class, that reinforcement learning's nomenclature is one of the easiest to understand, very self-explanatory in every sense of the word. What the name itself is what it is, okay? So the action is the action done by the agent which affects its state, that's the agent state itself, in the environment, okay? Like going back to the example of what we were talking the other day, I am the agent now and I am walking forward, right? So when I take one step forward, this me taking one step forward is the action that I'm taking in the environment, and the environment is the classroom here. And all of you constitute the part of the environment itself, right? You are obstacles which I'll have to navigate in order to get to any point in this room. Now, the change that happened to me from this style to this style is the state or the observation, okay? The agent needs to know its observation in order to know where it is and where it should go or should not go. So that is the observation or the state. Now, how the agent knows whether the action that it has taken resulting in a new state is a good action or not, or the state itself is good state or not, is through something called the reward. Reward is the return or the mathematical scalar return that the agent gets when it takes an action and changes its state in the environment, okay? So these are the most important terms in the reinforcement learning setup. So what exactly is reinforcement learning? Reinforcement learning, in the crudest sense, is trial and error learning, okay? So what the agent does is it will repeatedly take actions, different actions, staying in the same state to see how good or bad that is. Going back to the example of me going to that water bottle again, entering from this door, I know that every step I take forward or towards the bottle is a good action. Any step or any action I take that deviates me away from my goal, that is to reach that water bottle, is a bad action for which I might get a penalty, which is a negative reward basically, right? And how do I know whether I'm going good towards that bottle or not is through the observations that I see, that okay, I move forward, now the bottle gets closer to me, the distance reduces, right? Again, the distance reduces, so I'm taking good actions, good series of actions. So basically you take a reinforcement learning agent does something called sequential decision making. So it does a series of actions to complete a given episode in order to achieve its goal, okay? Yes?
So the action is randomly, or are you giving criteria set for that? The action is being taken by the robot or any other device?
Okay, yes. Now this is an interesting question. So the thing is, the action that the agent takes depends on the algorithm that you are using. Okay, in most cases. Okay, so what happens is initially when you don't know at all what the environment is or where your goal is or what kind of actions you should or should not take, you take absolutely random actions.
Does it take help from the previous experience because if you fail 2 or 3 times, does the new decision is based on the previous experience?
Absolutely, yes, correct. So when this happens over and over and over again, as the number of iterations increase, or as it is called episodes in reinforcement learning, as opposed to iterations in other paradigms of machine learning or AI, sorry, is that these episodes are stored. The episodic experience are stored in a buffer, which I will come to later when I talk about the other algorithms, which has experience buffer, experience replay. So there are different kinds of algorithms, and in few algorithms, you don't use the background at all, the experience at all. So you simply take new actions every time, and you learn from that action itself, right? So yes, but in some cases, the experience is stored, and experience is used to improve the performance of the agent, which is efficient because you don't have to take an action that you know is already bad because you already learned it's a bad action, right? So it's a trial and error form of learning. But the agent interacts with the environment through the actions to change its states to get a reward. That is what reinforcement learning is. Okay. I was talking about this slide the other day at the end of the class. Reinforcement learning is used for several applications. Like I said, the more complex, the better, right? The more use of reinforcement learning enhances in that kind of applications. Okay. Autonomous driving, autonomous vehicles, UAV, complex UAV tasks such as, say, going through a small window. You have a small window which is smaller than the width of the UAV itself. Okay, so now the UAV has to tilt and go forward. It can do at certain speeds, within a certain speeds, with classical controllers maybe. Okay, but then if you want to do it with different kind of speeds, it gets even more complicated with classical controllers. Or to assume a scenario where, say, there is a load that is slung to the quadrotor itself. By slung load, I mean this. This is your multi-rotor UAV, okay? You have a load, this is a rope, okay? So there is no direct control over this point. This load can only be controlled through the motion of the UAV. So you see how complicated the dynamics of the system become. UAV by itself is an underactuated system. What is an underactuated system? So it is something where the number of control inputs is lesser than the degrees of freedom of that system, right? So UAVs, multi-rotor UAVs in particular, have 6 degrees of freedom, okay? But they have only 4 control inputs. The 4 control inputs are roll, pitch, yaw, and the thrust, okay? So now when you add a rope, it adds 2 more degrees of freedom because now the load can swing in the longitudinal plane and the lateral plane. So which further complicates the entire system and the entire dynamics. So now classical controllers work in a very limited envelope of operation for this kind of systems. To fully use this UAV slung load systems or any complex systems, this is just an example I'm giving here, to fully utilize the potential of these complex systems, you need more advanced paradigms of control. And there steps in reinforcement learning, okay? And it is, like I said the other day, the robotic dog that you might have seen by Boston Dynamics called Animal, it is completely trained on reinforcement learning, which is very interesting, right? Because it can do very complicated and very interesting tasks very easily, just like how a real robot would do, right? You kick it, it would fall, but it knows how to come back on its feet. It'll simply come up and stand, which is fascinating, right? Is it not? So now coming to one of the most important slides in this course, entire course itself, okay? Why do we even need reinforcement learning, right? Control theory is there since many, many years, many decades. It has been working fine. There is whole industries working on it, like aerospace industry, process industry, oil and gas. You name an industry and it has been working fine with traditional controls. So why suddenly the need for reinforcement learning, right? Why? Because the tasks that we are doing with robots now is getting more and more complicated every day, right? And the environments or the setups in which robots are being used now is exponentially more different and complicated than what it was earlier used for. You had robots earlier as well, but mostly in factory settings with a fixed line, fixed setup, say in a production line where everything is fixed. But now you have the Tesla Optimus, for example, okay, which is a robot that walks with you, which will walk with you rather in the future, hopefully in the near future, or maybe not hopefully, I'm not sure. So those kind of robots are very complicated, right? Imagine that walking with you just like your friend. There's such a unpredicted and uncertain environment around it, but it will walk just like you walk. So for these kind of applications, you need something more advanced, more capable than traditional controllers, right? Hence, you need reinforcement learning. And now coming to the technical point of view as to why you need reinforcement learning, okay? So there is something called, there are two classes of systems, basically, okay? Nonlinear and linear systems, okay? Linear systems, as you might have studied in linear control theory, is something which has, okay, a system as simple as pendulum, okay? And pendulum system, you know a pendulum system, right? You have a pendulum hung to it, and it will swing like this with certain angle theta, right? If this pendulum swings within a very small range of angle capital theta, then the dynamics of the system can be linearized and approximated. In the coming slides, I'll talk about what dynamics are, what system modeling is, but just to give you an overview of why we need reinforcement learning and what linearized and nonlinear systems mean. So when this pendulum swings within a very small envelope of operation, then you have something called the linear regime of operation, where you can apply linear principles, right? Hence, you have linearized dynamics there. But assume that this pendulum swings to this angle, okay? Approximately, small angle approximation can be applied to angles within 20 degrees, right? Anything more than that, it might not be within the linear regime now, okay? Say angles of 85 degrees, that is well beyond the small angle approximation, right? So the approximation that we use, sine theta approximately equal to theta, might not hold if your angle is greater than, say, 20 degrees, or maybe conservatively 30 degrees even, right? So then in that kind of cases, you cannot use your traditional controllers like PID, LQR, or MPC, right? Then you need something more complicated. That is one of the reasons, okay? The other reason is the objective or the goal that you want to achieve with any controller has to be mathematically defined, right? In classical controllers, this mathematical equation has to be differentiable and continuous. So this constraint by itself limits the kind of mathematical equations that you can use to achieve your goal or achieve your objective, right? Whereas the reward function, that is the equivalent of the cost function in traditional control, so your reward function need not be continuous, nor it should be differentiable. It can be anything. It can be discontinuous. It can be whatever you want, right? It can be just a statement, or it can be simply a goal a number which you receive only when you achieve the objective. Otherwise, you get 0, nothing else, right? So it's so easy to formulate these kind of reward functions rather than a mathematically continuous and differentiable cost function, right? So yes, okay. Another thing is the modality, okay? When you're using classical controllers like say MPC or PID or LQR, those kind of controllers, the kind of inputs you can give to your system is limited. As in, those inputs have to be, say, numbers, and they can only be numbers, right? Whereas with reinforcement learning, say you're driving an autonomous car, right? If you have only number inputs, you can use a LiDAR sensor maybe, then get the input of the positions of different obstacles or objects on the road. Based on that, the controller will give you, say if you're using MPC, it will plan for a certain horizon and it will give you the control outputs, right? But that might not be the best case, right? Because there will be some things which you can see, but the LiDAR might not detect it correctly. Hence, reinforcement learning is a kind of controller where you can have whatever kind of inputs you want. You want images? Yes, you can have images, raw images as input. You don't need numbers. It takes in images as input, it will give you numbers as output, like say control action, like your acceleration should be 10% or 50% or brake 50%, whatever it is. But your input is an image, remember. You see the multimodality here? This is one of the most striking features of reinforcement learning. Have image input, number output, or have number input, whatever output you want. Words maybe, for example, as in the case of ChatGPT where you get words, right? So this is very fascinating and a very interesting and useful feature of reinforcement learning, okay? The uncertainty handling of these controllers, okay? Traditional controllers, they have a system for which they are designed, okay? And then a certain envelope within, beyond the region of that, say this is the domain of your system, okay? And if you find any term or any word that I use that is not clear to you, please stop and ask me, okay? This is the system that you modeled, okay? A traditional controller might work good within this shaded region, okay? But say if it is slightly outside this, then your traditional controller might not be very good at handling it, right? Whereas reinforcement learning based controllers with something called domain adaptation or domain randomization can be used for a very wide range of applications and operating envelope, right? With the same agent, you don't have to train it again and again, because say a controller, okay? How many of you are familiar with the concept? Yes.
The environment is like specific fixed region. That we are using either reinforcement learning or any traditional controller. So I think the controller will be better in fixed range to get stability as compared to the RA.
Yes, provided you know the system model exactly, and you can model the system exactly. But then a system as simple as pendulum, okay? There are frictions, there is air resistance, which you neglect everything when you're modeling a controller for PID, right? You don't consider friction, you don't consider air resistance, you don't consider that this rope is flexible, you assume that the rope itself is rigid. So you see the number of assumptions you have, and you assume that this point is frictionless, many different assumptions. In reinforcement learning, you don't need to do that. Because it learns from experience, whatever the response is, it will tune itself in order to get the optimal response for that operation or for that task on that system, right? So yes, this traditional controllers have a limited range of operation, okay? Whereas reinforcement learning controllers with proper training, like say with domain randomization or domain adaptation, like I stated, can be used for a very wide range of applications, right? Just one trained agent, and you can use for different applications, okay? How many of you are familiar here with the term adaptive controllers or gain scheduling? Okay, so I'll explain it. Say you have a process like this, okay? The process output is modeled this way, right? Now this is nonlinear, okay? So you cannot have one controller that will work from this point to this point. So what you need to do is, you need to segment this system into different operation ranges, okay? And then linearize for that range. Okay? So you get 1, 2, 3, 4, for example, in this case, you get 4 different regimes or 4 different operating envelopes. Okay? Clear? If I'm going fast, stop me please, and if anything is not clear, ask me please. 100% clear up until this point, right? Just to scare you people a little bit. These things might be asked in the midterm, okay? The only exam that you have. So now I'm assuming that I'll get more questions. Okay? So yes, so here now you break the operation into different operating envelopes, and then you design controllers for this. So you have, say you're designing a PID controller. You have PID 1, 2, 3, 4. Okay, you have 4 different PID controllers for one system when it is in different modes of operation, right? And it has to switch. Now every time the process reaches this point, it has to switch to the other controller now, okay? This is gain scheduling, also known as adaptive control, because now you're adapting your controller to different regimes of operation. Clear? Whereas with reinforcement learning controllers, you don't need all this. You can simply have one agent train for the entire set. That's it. And it will work. Okay? So you see how versatile that controller can be. However, reinforcement learning is not all glitter and glory. Yes?
For this nonlinear system,
Yes.
when you section a system into 4, are you now trying to make them to become linear?
Yes.
This one become linear?
Yes. That's the whole point. Okay, if I exaggerate this curve, it will be something like this. Say your system is like this. Okay? Now you segment it into different points, and each segment will be the tangent to this curve, and it will be linear. However, if you further zoom it, you will see that there are the extremes of that operating envelope might still fall beyond the actual system. See, it's not exactly on the system, because like what is a tangent? A circle. It will touch the circle only at one point, right? If your circle is of a larger radius, then it will be like this. It will seem exaggerated, but then still at the ends, it will not be on the process line itself, implying that that controller might not be the best controller for that particular operating range. And there will be switching as well, right? Switching of controllers, which might, even with the slightest of delay, might be critical in certain applications, right? Okay. So where was I? Okay, yes. Yes, reinforcement learning controller, despite all the advantages it possesses, it's not always the best. There are certain drawbacks, certain limitations. Yeah, not drawbacks, rather limitations of reinforcement learning controller as well, for most of which there is ongoing research to improve it, make it better. But then at least for now, yes, it exists. There are certain limitations that you need to be aware of and work around it or work with it. Okay? Now what are they? Training itself, training of AI agents in general, AI models in general, is computationally very expensive. Okay? Now, like I said, okay, yes, it possesses multimodality. Okay, you can have image input, you can have number output, but then when you're processing these images, it requires significantly higher computation power, right? But then with improving technology, now it gets better and better, and faster, smaller and cheaper. So everything is getting better, but then yes, it is computationally a lot more expensive than traditional controllers, because there you don't have images to take care of, right? You just have numbers, which are a lot easy to process, because images, they come in, you need bigger neural networks there to process it, and yeah, stronger, powerful, and it will take time as well. Another biggest drawback, I would say, of reinforcement learning is its black box nature. So the last class when we discussed about stability of this reinforcement learning controllers, that is one of the significant roadblocks in the adaptation of reinforcement learning, I would say, across different industries, right? So what happens is, reinforcement learning based controller, unlike classical controllers, don't have a fixed mathematical framework which will help you analyze the stability of the controller, right? So you cannot prove it mathematically that, okay, fine, if this happens, this happens, this happens, then this happens, hence the controller is stable, or hence the controller is unstable, right? No phase diagrams, no Bode plots, nothing. You don't have any such mathematical tool to guarantee the stability, right? So that black box nature and unstable, or rather no stability guarantees, go hand in hand, right? So this is one major limitation that is being worked in. Now where this is used, applications, they are, for now, because reinforcement learning has to be has to first prove itself that yes, I can work as a controller. So it is being used in the same places now where classical controllers might be used, but at the same time, to actually utilize or harness the full potential and power of reinforcement learning, it is used for very complex robotic applications as well. Okay, I'm stressing robotic again and again here because of the course nature. Okay, the course is reinforcement learning for control, rather control of mechatronic or mechanical and electrical systems, right? Because control again would mean it could be anything. It could be finances, it could be any field. Reinforcement learning as a controller can be used for a variety of applications and fields. But then the nature of this course is forcing me to use the term robotics here, okay? But don't think that reinforcement learning is a robotic controller only, okay? There are a few points of discussion which I'll do towards the end of the class. Now I'll move to the next topic, which is, now since I inquired last class that most of you, or rather a few of you don't have control background, or even in case you have and you took your control courses back in your bachelor's and now you might need a brush up, I'll just give you a brush up of what control topics we'll be going through or relating to in our reinforcement learning concepts, okay? Like I stated again, just to reiterate and re-emphasize that point, that we will be looking at reinforcement learning from a control lens here. Hence, you will be needing a background as to what control is, what control systems are, and how and where can we use reinforcement learning here, okay? So what exactly is control? In the simplest of terms, it means something that helps you obtain and maintain your desired target, okay? Your thermostat in this room is a controller, okay? Your cruise control when you drive your cars is controller, okay? Your oven when you cook, that the fixed timer is a controller, right? All these are controllers. But then now there are different kinds of controllers. There are two categories basically, open loop and closed loop control, okay? By open loop control, I mean something where there is no feedback, okay? Now say you have a car, you lock the speed at 110 or 120 kilometers per hour, okay? You're driving that car, no matter what the distance to the car in front of you or what the road conditions are, the car will maintain its speed of 120 degrees, right? There's a pothole, it will still go over 120 with that, right? Road is smooth, it will still go unless you don't brake explicitly, right? Why does this happen? Why does it not? There are new cars, say even, yeah, not fully autonomous driving cars, but then the newer cars have cruise control where you don't have to brake when there's a car in front of you. It automatically adjusts its speed. It slightly slows its speed so as to maintain a constant distance between you and the car in front of you, right? Why does it happen in that cars, whereas in few cars it doesn't happen? Feedback, right? Because there is feedback. So this car, say you have car A, car B, car A, car B. Car A don't have feedback, car B has feedback, okay? So when you get feedback, now the controller of car B is telling it that, okay, stop, there's a car in front of you, or there's a person crossing the road in front of you. You cannot go at that speed, lower your speed, right? So this is a feedback that the controller is getting from its perception modules, okay? Perception modules are nothing but the sensing mechanism of the system, right? So when there is feedback in the system, it is called a closed loop system. If there is no feedback, like the thermostat in this room, okay? No matter the number of people you have, if you fix the temperature at say 23 degrees, it will be at 23 degrees. Even if there's one person, it will be 23 degrees. Even if there are 50 people, it will be 23 degrees, right? Despite an intelligent controller there, or a controller with feedback might be like, okay, fine, there are more people in this room, it will be hotter, I need to reduce the temperature in order to maintain the same comfort of the inhabitants of that room, right? That is a closed loop controller. So you have open loop and closed loop controller. Reinforcement learning controllers are closed loop because you need to have observation fed to the reinforcement learning controller, right? So they work only in closed loop systems, okay? Okay. This is a very important diagram that you need to fully understand and be aware of. Okay? This has different components. You have the system, you have the controller. Okay? The two most important components. Then you have the feedback and your reference signal. Okay? And in some cases, you might have some kind of noise or some kind of disturbances. Finally, your output. Okay? You see how the system works? There's a reference input. Okay? You say the car, for example. Okay? Let's stick to that car example. You say, go at 120 kilometers per hour. Okay? Your feedback is the distance to the car in front of you. A very simple controller, right? It's say you have to maintain a distance of whatever, like say, I'm bad at distances, 10 meters maybe, okay? 10 meters between this car and that car. That car, if it is going at 120 kilometers per hour and you're going at 120, okay, that distance will always be maintained by itself. But if that car slows down a little bit, it goes to 118 or 115, then that distance will quickly reduce, right? So you might end up in a mishap, in an accident. However, if there is feedback and you say that, no, I want to maintain a distance of 10 meters between the two cars always, your controller will direct or guide the car to reduce its speed to maintain that same distance, right? That is what a closed loop system is, okay? What are the advantages? Obviously, it can handle robustness, right? When it takes feedback, whatever changes are there in that system, it will quickly adapt and react to that changes, right? So the question might arise, like, why do we even have open loop controllers, right? Because they're cheaper, simple. You don't need a perception module, right? There's no feedback coming in, so you're fine. Like say you are baking chicken or baking a bread or whatever, right? You know exactly that, okay, fine, this loaf of bread takes 12 minutes at this temperature to bake. You keep it in, set the timer, go, come back, take out your bread, it's ready. However, if you're baking it for the first time, you might end up burning the bread, right? So there, if you have a feedback mechanism, it might be better that, okay, fine, if the crust of the loaf of this bread is at this color, then stop. Or the internal temperature of the loaf is at this temperature, stop heating, that's it. But that would be too expensive, right? Because you have a very complicated feedback mechanism there. System dynamics. What are system dynamics? System dynamics is something that describes the way that system behaves, right? Now my hand, okay, it has certain dynamics. And I know that, that's why I'm able to grip this pen, right? And move it in a certain way to get certain patterns on the whiteboard, right? Say when I'm holding a very fragile cotton candy, for example, okay? I will not hold it with that same grip that I'm holding a hard pen, right? Otherwise, what will happen? I will simply end up squishing the cotton candy. That is soft, right? Because I have a feedback mechanism, my sensing mechanism of my fingers will tell me that, okay, fine, this is a soft object. Don't press it with the same intensity that you do for a hard object, right? So how do I control it? I get the feedback, but still how do I control it? That is through the dynamics of my fingers, right? I know that my fingers, if my nerves or my brain give a certain signal, it will move this way, right? This movement or this behavior of the system is dynamics, right? It's mathematically represented this way most often than not, okay? For continuous time systems. For discrete time systems, you will have t plus 1, obviously. And there are stochastic systems as well, right? Where you have the output of the system as a probability rather than a deterministic output, right? So these are the three kinds of mathematical representations of system dynamics, right? But system dynamics involve all the elements or all the components of that system. For example, a system as simple as a pendulum, okay? The friction, the tension in the rope, air drag, everything together will form the system dynamics, right? Often we use system dynamics and system model interchangeably, but they are not. System model, which you will come to know in the next slides, is the, what do you say, is the mathematical understanding of that dynamics, or rather, dare I say approximation, okay, because there will be certain terms which you will neglect, right? For something as simple as a motor, right, an electric motor, it will spin, it will have its internal frictions, internal mechanisms, many different things, but then when you're modeling that system, that electric system or electric motor system, you do it in a way where you simply model it as a first order system maybe, or a second order system at most. But then there might be many more degrees of dynamics, including say time delays or many different things, right? Is it clear? Or you want me to repeat this part? Clear, sure? Remember, exam. Okay? Now modeling, like I said, modeling is constructing or approximating that dynamics mathematically, right? You might have linear models or you might have non-linear models. So okay, like it's highlighted there, dynamics is the ground truth, the actual system, how it would exactly behave. Modeling is the approximation of that dynamics, right? Why do we use models? Because we want to design controllers and we need some mathematical equations for that, right? So having considering the entire dynamics might at times be redundant. You don't even need that, right? Because say you don't have to always consider the frictions, very small frictions, very small time delays or very small drags. All those things might be very, very small for all practical purposes, which might be simply negligible, right? And you might have heard this a lot, right, in your physics classes in high school, where you throw a ball, neglect air resistance, neglect air resistance. But there is air resistance, obviously. Simply by you neglecting it doesn't eliminate it from the real world. It's just that you decide to not consider it and model your system in a way that doesn't take that into consideration, right? Now, the types of model that you have can be divided into, apart from, okay, one way of classifying it is linear, non-linear. The other is how you get the model itself, how you obtain that model itself, okay? There are three ways, or rather three categories in this. A white box model, black box, gray box, okay? A white box model is something which is clear in the sense that you obtain it through physics of the system using classical proven theories like Newtonian mechanics, Euler-Lagrange mechanisms, or those kind of classical established theories, right? You see here, you have F is equal to ma, using the first principles, like using Newtonian mechanics, all those known equations that you have, known theories that you have. And then you have black box approximation or black box modeling. In this kind of modeling, you don't know the exact physics of the system, okay? Rather, what you do is, say, you have a person, okay? You have a person. You don't know what that person likes or dislikes. It's a small baby, okay? Assume it's a small baby, okay? You don't know what that baby likes or dislikes. So what you will do is, you will give it, say, a bit of lemon, see its reaction, and then you will be like, okay, lemon, good. Sugar, good. Chili, not so good. So you will model it this way. You basically give an input, see the output, and based on that you will model. And then if you have sufficient data, what you can do is, you can model that baby's behavior, baby's taste rather, that okay fine, this baby likes this things, so this is the model of that baby. I'll cook something which includes lemon, sugar and whatever, so you make a lemon pie basically, and you give the baby likes it. You add chili flavor on it, chili toppings, the baby won't like it, right? So this is how you model that system. This is a very raw, crude example, but I wanted to explain and emphasize what I mean here, right? Input, output, that are the only things that you know. What's happening in between, you don't know. Hence the term black box. Okay, it's completely covered, you don't know what's happening inside. Something goes in, you get what you want. Yes?
Like neural network, can we consider it neural network?
Yes, absolutely.
But if we get the data to the input and we the output, we know what is going within the hidden layer, like how much the weight is updated,
Okay.
what is the output.
Okay.
So on the basis of how much task function is applied, either is getting the value 0 or 1. So we know those information.
Yes.
But we do not know like what is exactly going in this process, but we know the mathematical step. Like
Yes.
one middle layer,
Yes.
from the first to the second layer, third layer. We know some high pressure is not completely big box.
You know the approximation of what is there inside. You don't know the physics of that system. By black box, I mean the physics of the system, right? Like say, suppose you have a ball, okay? You throw a ball. There are equations of motion which will tell you that if you throw at certain angle with certain velocity, it will follow a certain path, neglecting air resistance or including air resistance. In physics 101, you might have studied that, right? Like you throw a ball with a certain angle. If there is backspin, it will spin at certain angle. You can calculate the exact point where the ball hits, right? Just through the equations. Right? Assuming you don't know the equations, okay? What you do is you have a ball, you calculate its mass, okay? The ball is of this size, and you have a machine which is throwing with a certain fixed torque, okay? So you keep doing it again and again and again and again. You don't know the equations, but then if you do that enough number of times, then you will know where exactly the ball will pitch if you throw the ball with that arm or that robotic arm with this velocity or with this torque. You get my point now? That is what black box modeling is. You still will get exact input, exact output, but you don't know how it works there. Clear? Gray box modeling or hybrid modeling, where you have part known physics, part unknown physics, okay? Like in this case, the robotic arm, okay? You know the physics of the motion of the arm itself, okay? The torques and all those things, but then the frictions of the motors that you have in the robotic arm joints might be unknown to you, right? For that, you use a neural network, for example, which is a black box, okay? You don't know what's the friction curve, right? How do you get the friction curve? You simply do that experiment again and again and again and again with varying degrees of forces, and you plot a curve, and you plot a curve. Or rather, it might be something like this, like, okay, fine, as the force increases, friction increases, but after a certain point, it might decrease, right? You don't know exactly what equation it would be in terms of the physical world. You know the mathematical approximation of how it will work. So when you combine these two, you might get something called gray box approximation, which is being used a lot now, I would say, right? Or rather, it is being used, not a lot. Let's keep it that way. Another class of systems that we have is LTI and LTV, as in linear time invariant systems or linear time variant systems, okay? I use linear here, but it could be both, like it could be nonlinear as well. Let's assume it's time invariant and time varying systems, okay? What does this mean? This means a ball. Okay, again, let's get back to the ball example. A ball, no matter how many times you throw, assuming that there is no friction on the force on the floor and the ball doesn't deteriorate or degrade, the ball will have the same mass even if you throw it 500 times. Okay? But say you have a plane, okay, which takes off, has the same shape throughout the entire journey, okay, but it takes off with, say, mass x, okay. When it's landing, it's significantly lighter. It's x minus y, right? Why? Because the fuel, which is a significant portion of the aircraft's mass, is now burnt or used. So you end up with a very light aircraft, right? So these systems, the dynamics of the system change continuously as there is a continuous change in the properties of the system itself. These are time varying systems, okay? Time invariant systems are one which do not change at all throughout their operation. Clear? Time variant, time invariant. Yes, you have a question? Yes.
Rho will be considered as a time invariant.
Time invariant no. In terms of operation, it is time variant, okay? Because
In terms of mass, like
no, mass remains constant. Because yes, mass remains constant because the battery will go down in terms of voltage, but then the weight of the battery will remain constant. So yes. the drone here I wrote is not the multi-rotor UAV that runs with a battery actually. It is the big UAVs that run on fuel, fixed wing UAVs, okay? So sorry for the confusion about that. Now systems are analyzed in different domains, okay? Time domain and frequency domain. This particular topic might not be very or directly relevant to reinforcement learning, because there you will more often than not work with time domain only, okay? But then this, I'm giving you a brief, should you need it, where you decide to work on, say, controller stability, reinforcement learning controller stability, then frequency domain comes into play, okay? Because the stability analysis of systems is mostly done in frequency domain, right? So just as the name suggests, in time domain you analyze the time characteristics of the system, as in, say, again, the ball, okay? You throw a ball with a certain force. So how long does it take to reach its maximum velocity? How long does it take to reach a steady velocity? Or say you have a car, okay? You give a constant acceleration, so you see how it is going forward, okay? You suddenly give full accelerator and you stop. You see how it reacts. You constantly keep on increasing the acceleration throughout your journey. You see how it reacts. This is the time response of the car, okay? Whereas, say, when you are going through bumps and you simply are going through bumps or speed breakers, okay, where your car will now oscillate, okay? This will help you understand, not directly give you, but rather help you understand the frequency domain characteristics of your system, okay? Because there's something called resonant frequency, okay, which is the frequency at which the natural frequency of the system and the external frequency that is exciting the system coincides. When this happens, the oscillations of the system will be exaggerated. Anything below or above that, no, it will not be, okay? So that is why usually when cars are manufactured, they are done this test, okay, so that the suspension system don't ever come across the resonating frequency when it is going through bumps, because bumps or speed breakers usually have a certain fixed characteristics defined by law. They need to be at certain angle or certain characteristics. So most of them will have a fixed characteristic, okay? So the car, when it goes over that, will not hit the resonating frequency, hence it will not damage the car, right? Now, systems can be represented in different methods, one using transfer functions and the other using state space. One thing to note here is this kind of representation is primarily for linear systems only. You cannot have a transfer function approximation of a nonlinear system, right? Or a state space representation. You might have a state space representation, but transfer function, it will only be for linear systems, right? But when we are working with reinforcement learning controllers, we don't have to worry about this. We can simply mathematically obtain the equation of whatever the complex system is, sines, cosines, logarithms, exponents, whatever, it will work. Because reinforcement learning will not care about what model it is, it will work with linear, nonlinear, anything, okay? Just to explain you how to obtain the transfer function and the state space equations of a system, here is a very simple system, the mass spring damper system, okay? Mass times acceleration plus spring damping coefficient times the velocity plus the, no, sorry, that was the damper, this is the spring. Spring plus times the x, the position itself, okay? That's the system, and it is externally excited, hence u of t, otherwise it would be 0, okay? You have two, this is second order system. Why? Because the highest order or the highest differential in this equation is of order 2, right? So it's a second order system, implying you will be needing two variables to define that system, okay? So you'll have x1, x2. x1 will be the position itself, x2 will be the derivative of that position or velocity, okay? And then you can simply rewrite this equation in this regards like this. again, this is not a core reinforcement learning topic, but then since this is a bit of control background, I wanted to explain you this. You have m x double dot plus b x dot plus kx equal to u of u, since I'm not writing t for anything, assuming it's all in time domain. So now you have to obtain the equation for x double dot. X double dot is u minus bx dot minus kx the whole divided by m. Okay? And then you already have x double dot equal to x2. So now you can write the equations like this. You have x1 dot and x2 dot, which is x1 dot is simply x dot, x2 double dot is, sorry, x2 dot is x double dot, right? Because x2 was what? X2 was x dot. So x2 dot will be x2 x double dot. Clear? Okay. So you have x1, you define a variable now, x1 as x, and you define a variable x2 as x dot. Okay? Now from this equation, you obtain x dot, x double dot. Okay? This is simple algebraic manipulation. Okay? You get x double dot. For x dot, you already know that x dot is x2, which is x1 dot. Okay? So let me first write, okay, yeah, I think now I can do it, okay? This is like this, okay? So now you have Ax, this matrix is A, you have x, which is x1, x2, plus matrix B times u, okay? So x1, what was our x1 dot? X1 dot is simply x dot, so which is x2, so 0, 1, okay? And now here, rewrite this equation in this regard. It's u by m minus b x2 by m minus k x1 by m. Okay, so what's the coefficient of x1? It's minus k by m, and coefficient of x2 is minus b by m. And for x1, you don't have any u component. For x2, you have 1 by m, because u is already there. Okay, this representation is called the state space equation, a state space system representation, okay? And you have obviously the output y. In this case, you're assuming that the output is x2, so you can simply have x1 rather, 1, 0, x1, x2, and there is no external disturbance, so d is simply 0. Okay? Clear? This is how you obtain a system model in state space representation. Then you have the transfer function. Transfer function, you simply apply Laplace equation to this or Laplace transform to this. You get that in S domain, which I think I will skip, or you want me to do it now? Want me to do it, or is it okay if I skip the Laplace thing? Skip. Sorry? Okay, so I'll skip it. So you apply Laplace transform, okay? So now assuming 0 initial conditions, so this thing will simply become m x s squared plus b x s plus kx is equal to u. And then you have to simply get the equation in terms of y over u, output over input, and you will get this equation. Okay? Clear? So these are the two representations of the system that you have. This is slightly more in-depth topic, but then just I'll give you a very, very brief overview here. In reinforcement learning, you have two forms of algorithms, okay? Model free and model based. This is the only nomenclature in reinforcement learning which is slightly controversial, I would say. No, rather not controversial. It might be slightly ambiguous or confusing, okay? Model free is not model free in the sense that you will think it is. When I go into that, I'll go more in detail. Model based is again a different kind of model based, okay? Here you don't give the model to the system, the RL agent, rather the RL agent will learn the model itself, okay? Basically, it's the black box modeling. okay? Because the RL agent there will not learn the physics of the system, rather it will learn the approximation of the dynamics through input-output relation, okay? Hence it's model-based. Model-free, you don't technically need a model, okay? But then when you're training in simulations, obviously you will be needing some kind of dynamics which will mimic the system behavior, right? So there you will have a model, but yeah, when I come to it, I'll talk about more in detail, otherwise it might get slightly confusing. But just know that you have two forms of algorithms, model-free and model-based, okay? Again, these words that I have written here, sample efficiency, generalization, robustness, and safety. First two particularly, you will come across this a lot in this curriculum, in reinforcement learning curriculum, sample efficiency, generalization. Sample efficiency is the single most important thing for many different algorithms. As to why new algorithms even came into existence was to improve sample efficiency. Okay, what sample efficiency is, how it works, I'll come to it later in the subsequent lectures in this course. Now, how do you know your system is good or not in control terms? You will have something called the performance characteristics in time domain, which includes your rise time, peak overshoot, settling time, and steady state error. Okay? Out of these, rise time, peak time, and settling time, overshoot, are the transient characteristics. Settling time and steady state characteristics are the steady characteristics. Okay? In the sense, you have the system response like this. Now you see, within this region, the system has not stabilized, right? It is still moving, it is still transitioning into its final characteristic or final goal. Hence, this phase is called the transient phase of the system. And this is the steady phase, because now it has achieved its steady state, that's it. It will stay at that state until unless it is forced by an external force or input or whatever. So this time, what it takes, okay, now rise time will have different definitions according to different authors. Okay, different textbooks have different definitions of authors. One of the most standard one is the time it takes for the system to reach from 10% to 90% of the system's final value. Okay, this time basically. This time is your rise time. Okay, your peak time is the time it takes for the system to reach its peak value. Your peak overshoot is the maximum value the system achieves. This will be something very important for your reinforcement learning control as well, because that is how you will be tuning your controller, right? To improve this performance, you will need to reduce the overshoot, you will need to reduce the settling time because you want the system to settle as fast as possible. But then there's a trade-off, obviously. You cannot have everything fast settling, less overshoot. No, that will not be possible, right? Because physically there are certain constraints which will limit you to have a trade-off basically. Okay, fine. I will get speed, but I will not get very good efficiency, or I'll get very good efficiency, but I may not do it very quickly. Okay, it depends on the application that you're catering to. Certain applications will simply require a very fast output. They don't care how efficient or not. No matter how much it overshoots, they don't care. But then they quickly need to reach their steady state, right? So you have to make that trade-off. Rise time, settling, peak time. So yeah, sorry. Peak time, peak overshoot, and this time when it reaches within a 5% error or 3% sometimes, one of these values, like within 5 or 3% of the final value, that time is called the settling time, okay? And the steady state error is basically the error after the system is settled, and so the final response of the system and the desired target of the system, right? Or rather, the desired output of the system. So that difference or that error is the steady state error, okay? So now, why do we talk about this particularly and with such importance is because when you're designing your reward functions for reinforcement learning agent, you will have to design it in a way that you balance this trade-off. Speed and efficiency basically in raw terms, okay? As your system gets complicated, it might get more what do you say, interconnected, more complicated, but you will have to manage this trade-off based on the application that you're catering to or the system itself. Like the system might not be able to handle very large overshoots, but it's fine if it settles later, right? But then at times, no, overshoot, but settle quickly. So you need to manage this trade-off. Again, to the stability point. So stability of the systems with classical controllers or traditional controllers can be guaranteed through different methods, well-established methods, okay? But with reinforcement learning-based controller, you might not have that guarantees, right? But that doesn't mean that the system will not be stable. Okay? It might be stable, it might not be stable. But there's just no theoretical or mathematical proof or guarantee of that stability, okay? Different types of control strategies that you have, P, PI, PD, PID, okay? Basically, the first four are the derivatives of PID controller, okay? You have something called PID controller, proportional, integral, and derivative. So what you do is, you take the error and you pass it through three different paths. One is the proportional term, okay? So the error that you get, you simply pass it through a gaining scale, okay? Either it's a big number or small number, but the error directly, without any processing, passes through that gain. That is the proportional gain, okay? And then you have the derivative gain, where you take the error, you differentiate that error, and then it passes through again. That differentiated error that passes through this gain is the D term, okay? And then you have the integral term, where you integrate the error. This is primarily important, the I term, to reduce steady state error, okay? So you have, yes, the PID controller, okay? And that is one of the most commonly used controllers across industries, across applications. You name it, it will have a PID controller, okay? Oil and gas, aerospace, or whatever. Examples, okay, give me some fields where you think PID controller is used. Automobile, manufacturing, yes. Everywhere. You name that field, it will have PID controllers in it, okay? Now, the most important form of control that we will be focusing, something called optimal control, okay? Optimal control is a control strategy where you try to balance the control effort that you put in and the output that you get, okay? And more often than not, or no, rather, theoretical optimal controller will guarantee that you get the most optimal controller, okay? It will have something called a cost function that you need to minimize, okay? Which is very analogous to reinforcement learning based controller. There you basically have the inverse thing. You have a reward function that you will try to maximize. Here you have a cost function that you reduce, right? Optimal control, reinforcement learning control. They are very analogous to each other, okay? Reinforcement learning, in fact, is optimal controller, okay, is an optimal control obtained through learning or through machine learning or through trial and error, okay? Optimal controllers are obtained through different mechanisms like LQR, linear quadratic regulators, or MPC, model predictive controls. These two are theoretical or traditional controllers where you don't have any black box element in it, okay? You have mathematical equations which you will use to obtain your controllers, classical controllers, optimal controllers, okay? RL is a kind of optimal controller, right? Or it is an optimal controller which is obtained through learning. Clear? There you have a reward function to minimize, cost function to minimize. In RL you have a reward function to, what do you do with the reward function? Maximize, right? Yes.
So the optimal controller is a white box, right?
Okay.
It's built on models, right?
No, optimal controller is a theoretical concept. It is achieved through different mechanisms, namely LQR, MPC in traditional paradigm and reinforcement learning in the machine learning paradigm. So you can obtain optimal control itself is not a controller.
So it's a concept can be achieved by both.
Exactly. It's a concept that can be achieved through paradigms. Okay, traditional controllers, machine learning controllers. Okay, machine learning controllers, you will have reinforcement learning. Traditional controllers, you will have LQR or MPC. Okay, there's a lot of similarity or analogy between reinforcement learning and optimal controllers, even in terms of the terms that we use, the concepts that we use are very, very relatable to each other. Okay. A lot of concepts in reinforcement learning are inspired by by optimal controller, like concepts like which you will come across, Bellman equation and optimality equations, all those are inspired from optimal control. Okay. Yes, LQR is a method of realizing optimal control in traditional sense. You have the quadratic equation, quadratic cost function, quadratic y because you have x times x, right? Q is the what do you say? The performance index. R is the control effort, right? You have to balance between those two, and you have to solve something called an algebraic Riccati equation, right? This equation, as you see, is very complicated, right? So as the system gets complicated, it gets even more difficult to solve this algebraic Riccati equation. Okay. However, with reinforcement learning, you don't need this, and also you will see here that it has the term A and B. You recall what A and B are? Exactly, it is from the state space, implying it needs a model, right? It needs a model for obtaining your, here you have P, which will then help you obtain your controller gains. Okay, when you solve that equation, you will obtain the controller gains, which will be the optimal controller for that particular task on that particular system. Clear? But note here that you have the system involved here in the equation to obtain the gains. So if you don't have the model of the system, or you cannot model that system, then you might not be able to use your optimal controller, right? So yes, okay, like I said, you obtain the system equations, plug it into Riccati equation, solve for P. With that P, you get the controller gains, optimal controller gains rather, as stated there, and then that will be your control input. There's an example here which you can see. I'll not solve it obviously, because you will be needing MATLAB as well for that. Yes, okay, good point for this. From next class onwards, if you could bring your laptops, that might be helpful, because we might do some things in the class itself, right? To help you familiarize with, because we'll be using, and with MATLAB installed in it. MATLAB, Simulink, reinforcement learning toolbox. Okay, if you simply use the KFUPM license, you will get the entire toolbox. You can download all the toolboxes. Yes. Okay, yeah, you can download. You can email IT support if it is not easily available. They should help you get it. And as far as I know, yes, students do have access. Students do have access to that. Yes, so you can get it. Here, the function LQR is a MATLAB built-in function. So if you simply define this system and use this equation or use this function, you will get K, which is your controller gains. Okay, for a given performance index, because K depends on P, P depends on Q, and Q is your performance index. Yeah, LQR PID. PID basically is heuristic tuning. Okay, you simply tune the system like, assume you have a tape recorder, okay, or a tape system or a volume system where you simply turn the knob till you get a good sound you're comfortable with. There is no fixed rule as to you have to move it by this angle or you have to bring it at this point, right? You simply keep tuning it till you get the best performance for you. That is PID basically, okay? But LQR, no, it has a more mathematical sense to it in regards that it will tell you that, okay, fine, move it by this angle, you will achieve this sound which will be comfortable for your ears. Clear? Are these concepts clear? Any question? Okay. 100%, yes.
If your slides.
Sorry?
If your slides.
Okay. Yes.
Formal, before this.
Okay.
This, NPR, yeah. All this P something, I don't understand.
Okay. Here, this equation is called algebraic Riccati equation that needs to be solved to obtain the optimal controller gains for your controller for that task on that system.
But if we have
Sorry?
all these letters, we have any, yeah? This A, T, P, P, A, P, B, R.
Okay, I'll explain it. A is your system matrix that you obtained from the state space system representation. T here is the transpose of that matrix. P is what you're solving for. B is again your control input matrix. R is your control effort matrix. Q is your performance index matrix. So when you solve the, and T there are transposes. -1 is the inverses. Okay? So like I stated, you will be needing A, you will be needing B in order to obtain the optimal controller, which if you don't have, you will not be able to obtain the optimal controller for that system, right? Major limitation of this optimal controllers. For what systems do you have this A and B? For linear systems. If it is a nonlinear system, you might not again be able to use this, right? Because then A and B can be obtained for nonlinear systems, but the solution of the Riccati equation gets even more complicated when that A and B are nonlinear, right? So in order to overcome this limitation, we have to come up, or rather we decided to come up with something that uses data, right, which does not need the system model itself. So the terms that you will see here, we'll discuss them in detail later on, but then the parallels between optimal control and reinforcement learning is this way. Like you have the cost function, cost to go. In reinforcement learning, you will have something called a value function. Value function in its crudest sense of understanding is the cumulated reward that you get, basically the returns that you talked about, okay? Returns weighted in a certain way, cumulated in a certain way, but it's basically the returns in some sense, okay? Then you have Bellman optimality equation, and then you have the optimality here in, sorry, thank you. You have the control law here. The K that you obtain in LQR is the control law, okay? Whereas in reinforcement learning, you obtain something called a policy, which obviously we'll be discussing in detail. Okay, again an important concept, dynamic programming that you use when you know the model, but when you don't know, you will use value iteration. Okay, we'll be talking about that in detail again, obviously. So RL is generalization, RL for control rather, is a generalization of optimal control when you don't know the system dynamics, or the system dynamics are complex and nonlinear, and it involves uncertainty, randomness, that is stochasticity, that is that, okay?